Okay, hello students. Let's get started with the lab before wasting any time. And I hope you can. I would try to perform the tasks in easy steps, and I hope you could follow as well. And please remember that whatever you learn during this lab would be used in your next homework, which would be your second homework of data science, and the topic of today's lab is exploratory data analysis. So let's start with, I would open my Jupyter notebook, and then I would work on the file that I shared with you earlier. I have already saved the IPYNB, the IPython notebook file, in this lab2 folder. So here I open it, and okay, let's go. First you should read these guidelines. They are very important. You should download the first data set, which is about heart disease, from this link, and save it inside your lab2 folder. Then okay, because my computer name is my first name, so let me change the directory to the correct directory. So in the first step, as you can see, I'm just writing the location of the directory, then importing CSV library so that I can open CSV files, and then I'm opening the text file as a CSV, the data file, which is comma separated values, and converting all the values to a list. So this would actually convert it into a list of lists, where each list inside the big list is a row of data. All the so okay, let me run this, and all the rows actually contain some numeric values, which are numbers, but they are stored as strings. So in the first step, we would actually convert these strings to the to float values. Okay, so let's go step by step. Our first question is, how many rows are there in the data set? So let's count the rows. So you can count the rows by just checking the length of the list, which is in our case Cleveland underscore raw underscore data. Let me run this, and you can see there are 303 rows. If you want to check how many values are there in each row, you can check the length of any row inside this list. So that is, let's go raw underscore data. Since all rows are of the same size, so we can pick any row. Let's say the second list, which would be the third list, because indexing in Python starts from 0. So you can see there are 14 values in each list or each row. So we can say that there are 303 examples or instances or samples in the dataset, and each sample consists of 14 features or 14 fields or 14 values. Okay, so next we move on to the data cleaning. The first in this data cleaning, the first step is to convert all the values which are actually strings, but they are actually numbers but stored as strings. So that's, each number is inside quotes. So the first step is to convert these strings to numeric values or floats, and there might also be some missing values or some non-numeric values, so we also want to get rid of them. So we want to define a function which converts each value of input, which is a string, to a float, and if it's not a number, then we would convert that into none, which is again a float but doesn't have any value. So let's use a simple logic. If x is equal to the string, which is the question mark, then return none, else return float x. So else x would be returned, the number would be returned as it is, but it would be converted to float. So it's a simple function. You can run this function, and then you can create a new list where each value in the original raw list is converted to a float if it's a number inside quotes, and if it's not a number, if it's in question mark, then it would be converted to none. Okay, then we have the dataset summary, which are the column names of, so we have 14 columns, if you remember, so each column has a name. So let's form a list which consists of 14 characters or strings, each corresponding to a column name. So they are age, sex, CP, trust BPS, call, etc. And then let's zip these together to form a dictionary by the name header num, so that each in this dictionary the key is the name of the column, and the value is actually the index of the column, so which is 0, 1, 2, 3 and so on. Okay, next we define a function get call that takes a column name and returns the data in that column as a list of numbers. So let's try this. So we would return, let's say, X name. Okay, just a minute. Okay, so we created a dictionary with the name header num, which actually has the names of columns or headers as keys and values from 0 to 13, which are the numbers. So let's see how it looks like. Header num. Okay, so you can see that there is a key and value, or according to this header file and the corresponding index of the column. Okay, now next we define a function that would get a column from the data set, which in our case is Cleveland data, when we give the name of the column as the argument. So let's finish this part first. So we would like to return, let's call it X header num name, which would be our key for X in, and we want this for all of the rows, so Cleveland underscore data. So this function, when used with any name, name from the headers, would to return all the values for that column for all the rows. So let's run this. Okay, let's check what did we wrong. Okay, so there is a bracket missing here. Okay, and an extra bracket here, so let's remove them. Okay, we are good to go. Okay, now let's use the function that we defined to perform some basic statistical analysis on the dataset. Okay, so let's first get all the values for age from all the rows. So we would use the function that we defined earlier, and we would, instead of name, we would use age. So this would get us, this line would get us the ages of all the patients, and then we can calculate the minimum age, the maximum age, the mean age, and the standard deviation. So let's run this. You can see the minimum age in the dataset is 29 years, the maximum is 77, the average is 54.44, and the standard deviation is around 9. Okay, so this similarly you can have some statistical information about any column or any header accordingly. Okay, so moving on, next we define a function which would select a given column name and a predicate and returns the value of that column at rows for which the predicate is true. So there are two arguments, the column name, which would come from the header file, and a predicate, which would be basically a propositional variable. So if the predicate is true, and so that's why predicate would be a function, and if that's true, we would get the values for that column. If it's false, we won't get the values for those rows of that column. Okay, so we select the column from the column name, by the column name, and return the value of that column for rows when the predicate is true. Okay, in the next step we define a predicate function. Let's run this first, which is basically okay, let me correct this first. Okay, when for that column, for that certain column which we are using, if the value is equal to the given value of in the predicate function, then the predicate would be true and we would get the values of that certain column for a certain row or a certain patient. Otherwise it won't return that value. So we can use this predicate and the select function to filter our data based on some values. Okay, so we can use this now to filter the data based on age, where the sex column is equal to 1, or we can have all the values of ages when the sex column is equal to 0. So basically bifurcating the data set into two data sets, where one is for female only and the other one is for males only, and we would return their ages and then calculate their mean or averages. So you can see the mean age or average age for all male patients is 53.83, and the average age for all female patients is 55.72. Okay, so that's okay. So let's and so this is what you need to report here. Okay, now next, moving on, we would like to have some visualization of the data fields. We would start from the histograms. So what values are frequent, more frequent, and what values are less frequent. We would like to see that using a histogram. So for that we use PyLab library of the matplotlib, and we are using 30 bins. So if we run this, okay, here is the distribution of the data with respect to age. So as you can see, most of the people are around here in the later ages, and there are less number of people are around here with less ages. Because it's a patient's data and mostly with the heart disease, so we can expect this result. Okay, now for the same patients, we now let's plot the histogram for the blood pressure. So as you can see, we have another histogram which shows the distribution of the blood pressure for different ages, and you can see for different people, you can see for most people the blood pressure is in the lower range, and you can see this is skewed distribution, and it's negatively skewed because it's skewed on the negative side or on the left hand side. The first one was a positively skewed distribution, not much skewed but still a bit skewed, but this one is more skewed towards the left, towards the lower values. Okay, so the task is you have to describe the rough shape of the distribution BPS. Is it skewed? And so you can see it is skewed, and it's kind of a bell shape, but it's very skewed, and we can see more fine results if we increase the number of bins. For example, let's say if we increase the number of bins here from 30 to 60, you can see they are more finely distributed. Same data set, but there's just a different representation. Okay, moving on. Scatter plots, where we can plot one value against another value. For example, we can plot age versus blood pressure or age versus the heart rate, and it would be, and the plot would be in terms of points at different places. So it's a two-dimensional plot. So let's first try this one. You can see for different ages you have different blood pressures, and there is a trend. There is a slight trend. You can see that for higher ages, the rate of blood pressure is also a bit high. Okay, then we can do the same thing with heart rate, and you can see with increasing age the heart rate is approximately, in a way it's decreasing, so there is a trend here as well. And it's, although it doesn't seem very linear, but we can fit a line. So an approximate linear regression we can perform, where we can see how much is the blood pressure or the heart rate affected by age. Okay, but before that, let's also use another variable, which is num, which is basically the stage of disease, or the stage of heart disease, or the its value, and the values are between 0 and 5. So if for example, if a person is completely fine, if his health is completely fine, this number would be 0, and as severe the heart disease is, the number would be higher and higher, up to 4. So we can, so in this plot we would, let's try this. We are again plotting the blood pressure against age, but for different types of the heart disease we are using different colors to represent it. So you can and that there are more yellow dots on the right side and more blue dots on the left side, and let's see which one, what color means what. So you can see the yellow is the high value, which is 4. So that means higher, the people with higher age are more likely to have a higher heart level of heart disease. Excuse me. So so you can see there's you can analyze these plots, and you can also answer these questions. They are very easy. Okay, moving on. Let's convert these values, age and BP, to arrays, so that we can perform some more experiments. For example, we want to fit a line to these values, so we can perform a linear regression. So that is, we are using the polyfit function from the NumPy library to calculate the slope and the intercept m and b, and then plot the line on top of the scatter plots. So let's do that. So again you can see the same scatter plot which we plotted before, where we have blood pressure versus age, but now we are also having a line on top of the plot, a scatter plot, which shows a trend. And as you could expect, the line has a positive slope, which means people with higher ages would more likely to have a higher blood pressure. A similar thing we can do with the heart rate, and you can see there is a negative slope with the of this line, and which means that people with higher age are more likely to have low heart rate. Okay, so up till now it's very straightforward, very easy. Just some tweaks and you can understand the data, and we usually perform such tasks or such process when we do mostly any type of data analysis, so we can have an overall look at the data, how the data behaves, for example. Okay, in the next step, we would perform some more advanced experiments, not much advanced, but a bit more, and where we would analyze some more fields or values from the data. For example, uh, uh, okay, we in this one, let's perform this. We are actually plotting um, BP versus uh, the stage of her disease, which we didn't do before, and then fitting a line on that. So as you can see, there is a positive, there's a line with a positive slope, so which means that uh, with the with higher BP, the or you can say the actually the stage of heart disease is positively correlated with high BP. The question is based on this plot. Do you think the blood pressure influences heart disease? So yes, it shows just based on this plot only. It shows that the blood pressure influences heart disease. But it always remember that correlation doesn't necessarily means causation. So it doesn't necessarily mean that the heart disease is because of the high blood pressure or the high blood pressure is because of the heart disease. There might be another common reason for both of them. So they are positively correlated, which means lower blood pressure means lower heart rate, and high blood pressure means higher heart disease, but they are not necessarily have a cause and effect relationship. Okay, moving on. Now we change the factor from BP to age and see if there is any relation, any influence of age on the heart disease. So again, you can see there is a positive influence of age on the heart disease, which means people with higher age are more likely to have heart disease. And so we can also expect that there is a relation between BPS and the rate of and the level of heart disease as well, combining these two results. Okay, so in next step we would want some dimensionality reduction. That means that you, instead of using the 14 parameters, we would like to reduce them to a small number of parameters which are more uncorrelated or independent from each other using PCA or principal component analysis. We would cover the PCA in a bit briefly in our lectures as well, but for now just remember that PCA is a method to reduce the number of factors or reduce the number of dimensions in a data set, and it basically generates new features which are actually derivative are derivatives of the original features. So it's in a projected vector space. So for example, we are in this example we will be moving from 14 dimensions to 2 dimensions only, the most relevant or the most influential dimensions. Another thing we are doing here is we are reducing the number of dimensions before applying PCA to 9 by removing all the columns where there are values, where there are unknown values. For example, if you remember in the beginning, we replaced some values which were unknown by none. So here we are completely removing those columns. So we are using just first 9 columns of the data, Cleveland underscore matrix, and then we apply PCA on it. Okay, here I want to do some changes because at my PC I don't have the matplotlib mlab library, so instead I would use sklearn because I already have that, and sklearn.decomposition import PCA, and then there is a bit change to how we use this PCA, which is PCA and number of components equal to 2. And then we apply the PCA on the data set by using the fit method, and then get the results by using the transform method. So let me change this to a small PCA and PCA dot transform. Let me copy this again here. Okay, so this would give us the YY would be actually a two-dimensional array. So it would have 303 rows and only 2 columns. And okay, so let's first run this, and then now we only have 2 values in each row. So let's have a scatter plot. So this is our scatter plot, and you can see there is a correlation between these 2 values. For example, as the first value increases, the second value also increases, and which would be actually the answer to your next question, which is, do you see a relationship between the 2 main variables x and y axis of this plot? And so the answer is yes, there is a relationship, which is actually positive. Okay, that's the first part of the lab. The next part is about some text data. So let's first do this, and then we would continue with the next part.